I'm Saud, and by the end of this video you shall understand how the ALU implements Booth's algorithm to multiply binary numbers. The ALU cannot simply multiply numbers, it can only add, subtract and shift. Booth's algorithm is a means of achieving multiplication by performing addition, subtraction and shifting. Let's multiply 6 and 2. We'll multiply these two numbers using Booth's. The first thing is we'll write the binary equivalence of these two numbers. So 6 is 1, 1, 0 and 2 is 1, 0. Now the first bit indicates whether a number is positive or negative. 0 indicates that a number is positive and 1 indicates that a number is negative. I place 0 before 110 to indicate that 6 is a positive number, and since these are like 4 bits, I'll place 2 more zeros before 10, and now even 2 is of 4 bits, and this first bit of 2 indicates that 2 is a positive number. I'll perform these steps, and with that it'll be clear how Booth's algorithm works. We need 4 registers. The first is the accumulator, the next is the multiplier, that is Q, and our multiplier out here is 2. The next is the Q minus 1 bit. It will hold only 1 bit at a time, this register. And the next is multiplicand, and our multiplicand out here is 6, so that is 0, 1, 1, 0. Now initially A holds 0. I'll write 4 zeros out here. Q will hold the multiplier, and that is 0, 0, 1, 0. Initially our Q minus 1 bit is 0. So this is how we have it initially. We'll place 0 and 0 in the A and Q minus 1 registers, and Q will hold the multiplier, that is 2, and M will hold the multiplicand, that is 6. Now since we have 4 bits, we shall perform 4 steps, and the final step shall give us the answer. So this is the space for my first step, this is for the second step, this is for the third step, and the final step shall give us the answer. The next thing we shall do is we shall compare the Q0 and the Q minus 1 bit positions. I'll write it out here. Q0 and Q minus 1. This 0 is the Q0 position of Q. This 1 is the Q1 position. This 0 is Q2 and this 0 is Q3. So initially our Q0 and Q minus 1 are 0 and 0. Whenever both of them are same, that is either both of them are 0, 0 or 1 and 1, we'll simply shift. The shift that we perform is the arithmetic right shift. In that we get the first bit of A as it is, we get it down. In the second position we again get the first bit of A, and for the remaining positions we start from the second bit of A. So this will come down, then will be this bit, then this 0 shall come over here, then it will be these two zeros, then this one will come over here, and this Q0 bit position comes in the Q minus 1 position. This was our first step, and all that we did over here was shifting. Now we'll again compare the Q0 and the Q minus 1 positions. So we have 1 and 0. When we have them as 1 and 0, we will subtract M from A, we'll perform A minus M, and we'll store it in A. And if we have them as 0 and 1, we'll add A and M, that is we'll perform A plus M, and we'll store that value in A. So out here we have 1 and 0, so we'll do A minus M, and we'll store the value in A. So 0, 0, 0, 0, that is A, 0, 0, 0, 0 minus 0, 1, 1, 0, A minus M shall give us 1, 0, 1, 0. You can do this using the 1's or the 2's complement method, or you can simply use a calci. If you are using the calculator, then just select the last 4 bits and write Q down as it is, so 0, 0, 0, 1, and even this 0 will come as it is. So this was the first step of our second step. The next step will be shifting, so we'll do shifting again. This 1 will come down as it is, this 1 will again come over here in the second position, then this 0 comes down, and then it is this 1. So our new A is 1101. Then this 0 will come over here. Then these three zeros. So it's 0, 0, 0. Then this 1 comes over here. Our second step is complete. Our new Q0 and Q minus 1 values are 0 and 1. Q0 and Q minus 1 bits are 0, 1. So we'll do A plus M. And we'll store that in A. So 1, 1, 0, 1 plus 0, 1, 1, 0 will give us 0, 0, 1, 1. So this is the A plus M value, and we are storing it in A, and Q will be carried down as it is, so these 4 zeros will come down, and then this 1. The next thing we shall do is we shall shift. So this 0 will come down as it is. Then even in the second position we'll have the first 0. So in the third position we'll have the second 0, and then it'll be this 1. Then this 1 will come over here, so it's 1, and then 3 zeros. The last 0 of Q, that is Q0, will come in the Q minus 1 position. So this 0 will come over here. And this was our shifting. So our third step is complete. Next we'll again compare Q0 and Q minus 1 positions. So we have 0 and 0. When we have both of them same, that is 0 and 0 or 1 and 1, we'll simply shift. So this 0 gets carried down. So this is 0. Then this first 0 will again come down over here. So this is 0. Then these two zeros, so it will be 0, 0, 0, 0. This 1 will come over here. Then will be this 1. This 1, 1, and then these two zeros. And our new Q minus 1 will be this 0. And with this, our last step is complete. The combined value of A and Q is our solution. So this is our answer. 6 into 2 is 0, 0, 0, 0, 1, 1, 0, 0. And if you see it, if you check it, this 0 is 2 raised to 0, this 0 is 2 raised to 1, this 1 is in the position of 2 raised to 2, and this 1 is in the position of 2 raised to 3. So 2 raised to 3 is 8, and 2 raised to 2 is 4. 8 plus 4 is 12, and 6 into 2 is 12. I'll quickly go through all these steps again. Initially A holds 0, and even Q minus 1 is 0. Q holds the multiplier value, and M is the multiplicand. Then we'll compare the Q0 and the Q minus 1 bits. So we had 0, 0, and that is why we simply shifted, and on shifting we got this. Then we again compared Q0 and Q minus 1. We had them as 1 and 0. When we had them as 1 and 0, we did A minus M, and we stored it in A. Then again we shifted. Next we again compared Q0 and Q minus 1 values. We had them as 0 and 1, so we did A plus M, and we stored it in A. Then after that we again shifted. We saw a new Q0 and Q minus 1 values. They were 0 and 0, so we again shifted. We performed 4 steps because we had 4 bits. And in our last step, the combined result of A and Q gave us the answer. Now in case you have one of the numbers negative, or if both of the numbers are negative, suppose minus 6 is negative, then you take the 2's complement of 6, and that will be in the position of M. Perform all the steps as they are, and then in the final, when you get the result, then just take the 2's complement of the result, and that will be the answer. This was Booth's algorithm. Thank you very much for listening, and I hope you benefited. A slight addition to the previous video: when we have both the bits same, that is Q0 and Q minus 1 are 0, 0 or 1 and 1, then we shift. And when the bits are different, that is Q0 and Q minus 1 are either 1, 0 or 0, 1, then we do A minus M or A plus M. So when we have them as 1 and 0, we do A minus M, and we store it in A. Now an easy way to remember this is 1 minus 0 is easy to perform in terms of binary, and 0 minus 1 is difficult to perform in terms of binary. So when it is difficult to perform subtraction, then you do A plus M, and you store it in A. And when 1 minus 0, since it is easy, then you will do A minus M. 0 minus 1 is difficult, so you will do A plus M. It doesn't really make sense, but it is easy to remember it this way. I hope this benefits you.